Okay, today we're going to go over the Taylor polynomials. The equation is f of x over n to the factorial times x minus c to the n. N is the number of derivative that you're on, and c equals the center. If it's the Maclaurin series, then c is always 0. So you're going to take f of x and do the first derivative, then the second, then the third, then the fourth, etc., until you reach the number of degrees indicated or number of non-zero terms. So let's do an example. Let's use e to the negative x squared, and we're finding the 6th-degree polynomial. You could either do writing out each derivative and then plugging it into the equation on the first page, or you can use the series that we already know from flashcards. So let's do e to the x. Here's the series given, and here's what it looks like when it's plugged in. So now you're going to plug in negative x squared for every x, as shown. And it's going to come out to this. And it's going to equal this. And this whole thing, as indicated in the problem, is to the 6th-degree polynomial. And that's how you do it.
LaGrange error is the remainder of Taylor polynomials. The LaGrange error formula is r sub n of x equals the max of f raised to the n plus 1 z over n plus 1 factorial times x raised to the n plus 1. For example, we're going to do the 4th degree Taylor polynomial of f of x equals cosine x about c equals pi over 6, and we're going to find the LaGrange error. So we know that we're going to do r of 4 to the 0.5, sorry, x equals 0.5. It's going to equal the max of f5 to the z all over 5 factorial 0.5 raised to the 5th. So r sub 4 of 0.5 is going to equal the max of absolute value of negative sine of x, which is the 5th derivative of cosine x, all over 5 factorial times 0.5 raised to the 5th. So that's going to equal 1 over 5 factorial times 0.5 raised to the 5th, which is going to equal 6.099 e to the negative 11. And that's how you do the LaGrange
series
error.
remainder is a part of the Taylor polynomial series and everything like that. This is the formula for it. It's not required that you know it exactly because we never followed this in class, and it's not really asked for it to plug into the AP exam. You don't necessarily need it, but if you are a formula person, this is the one you have to memorize. What you have to write, because most of these are going to be free response questions, you always have to put, because it is a convergent alternating series, that's how you start off your answer, and it has to be put there. The first neglected term, for example, a sub 3 or whichever number, is equal to some fraction which is less than the remainder that they asked for. And they'll always give you that number in the problem. So in this example, natural log of x squared plus 1, determine the rational number a such that the remainder is less than 1 over 100. So that's the remainder that they gave you. So like in that explanation, that's what you'll put. So for this problem, you're going to have to solve for the x so you know what to plug in to see which is the remaining term, the first neglected term. So 5/4, which is what they gave you here, is equal to x squared plus 1. You solve for x and get it to be 1/2. So you got to write out your first few terms of the Taylor polynomial series, and then you're going to plug in x. So 1/2 squared, and so on, like that. And when you get your numbers, it comes to 1/4 minus 1 over 32 plus 1 over 3 times 64. And you automatically know that that fraction is less than 1 over 100. So you see, and it's your third term, which is going to be your first neglected term. So in your explanation, all you'd have to write is, because it is a convergent alternating series, a sub 3, which is 1 over 3 times 64, is less than 1 over 100. And that's all you have to do for the alternating series remainder.
So for series convergence, there are 6 main things that you need to remember for the AP exam. The first thing is the p-series test, which looks like this. If p is greater than 1, then it converges. If p is less than 1, then it diverges. The second thing is the ratio test, and you use it to find the interval of convergence. So you do the limit as n approaches infinity of a sub n plus 1 over a sub n, and then you get something like this, which is like the absolute value of x minus 1 is less than 2. And this part is the center, and here's the center is at 1, and this number is the radius of convergence. So your interval of convergence is -1 is less than, or x is greater than -1 and less than 3. And then you need to check both endpoints. The third thing is the geometric series test, and it looks like this, and x is usually like a fraction. If x is less than 1, then it converges, and if x is greater than 1, it diverges. And to find the sum of a geometric series, you do a sub 1 minus over 1 minus r. The fourth thing is alternating harmonics, and they all look like this. So if you see anything that looks like this, then it always converges. The fifth thing is the harmonic series, and these two equations are harmonic, and they always diverge. The sixth thing is alternating series test, and if either of these two things are true, then it always converges. Okay, now here are some examples. Which of the following converges? So you look at these three, and you can automatically cross this one out because the fraction is greater than 1, so it diverges. For this one, you can do the integral test, and you get this equation, 1/2 natural log of n squared plus 1 from infinity to 1. And you plug in infinity, and it automatically diverges. And then for this one, we know that it's arctangent of n, and you plug in infinity, and arctangent of infinity is always pi over 2. And then you plug in arctangent of 1, and it's pi over 4. So pi over 2 minus pi over 4 is pi over 4, and it converges. This example, it's asked, what are all the values of x for which the series converges? So, you do the ratio test to figure out the interval of convergence. So, you do the limit as n approaches infinity of a sub n plus 1 over a sub n. And you get your interval of convergence as -1 is less than x is less than 1. And then you need to check the points. So when you plug in -1 for x, the bases are the same, so you add the exponents. So you get -1 to the 2n over natural log of n, and that will always be the same, so it diverges. That will always be positive, so it diverges. And then you plug in a positive 1, and it alternates because you're left with -1 to the n. So that one always converges. Yay!